Now this curve that I have dotted, it still was all right to say that a black body emits frequency at all different wavelengths. But as the wavelengths approach zero frequency, I'm sorry, do I have this? Yeah, sorry, this is, my bad. Sorry, this x-axis is wavelength. As the wavelength approached zero, then what happened to the energy is it would shoot up to infinity. Okay, but we knew through experimental evidence that the true black body spectrum, okay, that looks more familiar, more like what we're used to seeing. Okay, we know that it has to have a finite area underneath this curve. Okay, we have to have a finite energy to the amount of power that can be radiated by a body at a certain temperature. What's that? No, it's instead of diverging to infinity. That's true, but with calculus, when you have if you have an asymptote, it actually results in a finite value.
Because it gets so close to zero?
Yeah. Because there's, yeah, it predicts a finite value even when it's an asymptote.
It's just going to infinity.
That's right.
No, when it's going to infinity, once infinity is small, it's zero.
Yeah. It can't go any further because it's getting so close to zero.
Okay, so here's where we are right now, just to catch you up in case you were dreaming there for a second. We have classical physics saying that the energy of any black body is going to be infinite. Anything that has temperature has to have an infinite amount of energy. Not quite. So, completely disagreeing with the observed experimental evidence for a black body. Now, in walks Max Planck. Okay? Literally a magic person can see. You guys are wrong.
Let's show you some big and small numbers.
That's right. He was actually hired. He was hired by a German light bulb manufacturer to create a more efficient bulb. Okay, they wanted the peak of that black body. Remember, here's the visible spectrum. They wanted the peak of the light bulb's emissions to fall more within that visible spectrum to create truer white light with less power. But in order for him to do that, he had to go back and revisit this ultraviolet catastrophe and see why it's wrong. Okay. So he found that this can work as long as we abandon the fact that there's an equal probability, going back to the previous page. Okay. Whoops. If we abandon the fact that there's that equal probability of molecule vibrating at any harmonics, we can fix this ultraviolet catastrophe. Okay, so now we're into Max Planck's contributions. Oh, 2 was the ultraviolet catastrophe. Sorry.
It was number 2.
Sorry, guys. That was 2. well, maybe the energy of these vibrating molecules isn't continuous. Maybe they can only have discrete energy states. We already knew that electrons have discrete energy states, so why can't molecules have discrete energy states as well? It ends up being true. Okay, so he experimentally verified this energy by plugging in, and this was trial and error. He got really, really close to it, but he came up with Planck's constant. Yeah, it's all constant.
Make that for himself. To do that by trial and error.
What's that? That's super small. There's a lot more with Planck's constant. Planck's constant is still coming into theories like string theory. They're still using it to show that to discuss the actual size of the super small building blocks of the universe. Thank God we don't go into string theory. Oh boy, that is next level stuff.
That stuff is needed.
What's that? Oh no. No, you can't even talk about string theory without having a really good understanding of calculus.
Isn't it like super like theoretical anyway? Like
It is, yeah.
it's
That was going to be my topic when we did we're going to do the TOK presentation during lunch, but we have a guest speaker instead. But we're going to talk about how theoretical physics is about 200 years ahead right now of what can be experimentally verified.
exactly.
That's nuts. Robbie, you had a question?
Planck length, the smallest.
It's the smallest theoretical point in space. Yeah,
That's awesome. And then there's like Planck time as well. That was cool.
that's right.
It's like smallest possible like time an event can happen in.
That's
Something
right.
like that.
Yeah, the best ideas now are saying that the universe is discrete in nature at that scale. It's like points in a grid, and nothing can exist between those points at that scale. Yeah.
So that's the smallest possible.
That's the smallest possible number, yes, in the universe.
Oh,
Yeah. I mean, you can make smaller numbers, but smallest possible existence of a number, I guess. Okay.
yeah.
Where was that?
So.
Okay, he also assigned the probability of a molecule vibrating at one of these higher modal vibrations, or higher energy states. Instead of having an equal probability to lower energy states, he applied a previous statistical phenomenon, is now called a Bose-Einstein distribution, but it was in existence before that. It's kind of hard when you're reading about this stuff to actually order because these discoveries all became really quick in succession. This discovery was before Einstein took over the lead for quantum physics, but it also said when I was reading that his discovery was based on what's called the Bose-Einstein distribution of probability. So I'm still a little confused as to what came first, chicken or the egg in that case. But I think there was an earlier, before it was called the Bose-Einstein probability, it was probably based on some earlier probability studies. Anyways.
You would have went off researching for that.
That's right, yeah. Okay, so I'm going to give you the final equation, okay, but I just want to be clear that it's not curriculum, okay? I just want to show you the final equation that Planck came up with to model the intensity.